Hello, Go WestConf. I'm Robert Burke, and this is Go Without Generics, a retrospective. In this talk, I'm going to look at some of the code patterns we needed to do the job of generics before we had them. Back when I submitted this talk, generics in Go had not yet been scheduled. We only had the 2019 draft design as part of the Go 2 discussion. That design has evolved, and now we have a timeline for the next step for generics and an experimentation tool. I couldn't be more excited. Square brackets for the win. But what are generics, and why do we care? The draft design defines generic as a shorthand to mean a function or type that takes type parameters. Don't confuse the term generic as used in this design with the same term in other languages like C++, C#, Java, or Rust. They have similarities, but are not the same. The way I put it is that we use the term generic as a shorthand for writing less code. We want to be able to treat the types of certain values generically, rather than specifically. For the first 10 years of Go's life, it has been a very specific language, and this has been part of its charm and power. It's powerful to be able to read code and have no need to overthink what it is doing. Go's magic is that it's accessible without understanding everything beneath the call. You know you can trust what is happening with a given snippet of code, since there are no overloads, there's no inheritance. If you know the type, you know what it's going to do. Because Go treats most of its types specifically, it lets the compiler be fast, and enables the compiler to make your code fast. But that specificity has its downsides too. One tends to repeat the same code over and over. Useful and efficient data structures need to be rewritten to support new types and uses, and this can lead to mistakes. What generics do is trade clarity for convenience. You lose the notion of the exact type your code is dealing with, in exchange for not needing to repeat it. This is subtle, of course. It can be said that stripping out the type makes the code clearer, because it says the specific type doesn't matter. So the trade-off will vary. But that's me getting ahead of myself, talking about real generic code. What this talk covers is the time before then. My goal today is generic function invocation. That is, calling a function without caring about its type. What did we have to do? And post-generics, can we do better? Since we have to start somewhere, let's start with pattern 0, ordinary Go. There's nothing fancy here, just a few function calls that we're composing together into a short pipeline. Let's try removing the types from this code and make it generic. The types are evident in their function signatures, and by calling them directly, we can see the clarity and simplicity of Go in action. The direct function only mentions types for its parameter and return type, but otherwise, Go lets us elide those types, leading to clear and understandable code. If the program type checks, there's no need for the reader to really know what foo, bar, or baz are doing. But you can tell that because of the way that the variables are passed around, foo's return type matches bar's parameter type, and bar's return type matches baz's parameter type. So it's all related. But my question is, how can we call these functions generically? Well, what about type assertion? Type assertion is a feature of Go interfaces to assert that a given interface variable is actually a specific type. If it's not, the program will panic. There's also a safe version that doesn't panic if the assertion is wrong, but we're not going to be using that one today. So let's try stripping the types from that code, starting with the variables. That didn't help. We've ended up with more types everywhere, and we can't really say this code is generic. Let's try that again, but with the functions themselves. There we go. That's a bit better. The pipeline code is certainly much cleaner, but now the function code is messier, since we need to assert the interfaces back to their types. One exception to note here is baz2. It's arguably fully generic on its parameter type, since it since its implementation never cared about what type it was handling anyway. Funct sprintf and similar functions are the same. So now I need to be clear here. This is perfectly reasonable Go, but it's dissatisfying. We've had to abandon all our compile time type safety and turn it into runtime type safety. Unfortunately, we'll have to abandon the compile time safety for the rest of this talk. On the other hand, we can now make our pipeline code generic. Look at that. Isn't that clean? Unfortunately, it also doesn't compile. Go doesn't automatically convert types, and there's no exception around calling these interface values. But our earlier transformation to our functions did bring us closer. All of our functions now have the same type signature. And since we've made them all the same type, our pipeline can call them all the same way. So this is where the story could end. As long as we make every function conform to this type signature and carefully ensure they're in the right order, we can invoke any series of functions in our pipeline, calling one after the other. But of course we're not done yet. Next up is reflection. The concept of reflection is the ability of a program to examine its own structure, particularly through types, and it may hold the key to the metaprogramming I'm looking for. I strongly recommend reading the official blog post and the documentation for the Reflect package in the standard library for more details. With this variant of the code, we end up with a little bit of a mess, but we don't need to follow through with the interface indirection of our functions. We just need to convert our functions into reflect.values using reflect.valueOf, call the call method on that, and passing in a slice of reflect.values for our parameters. So this is closer to our 0.5 type assert pattern I showed you, in that the reflect library takes care of the type assertion for us. And with a little adjustment, it's also more powerful too, as long as the outputs of one function match the inputs of the next. We can even adjust the pipeline functions nearly however we like. But reflection has a cost, and with such simple functions, it really adds up. Fortunately, we can measure that cost pretty easily using the built-in Go benchmarking tools. Unsurprisingly, the direct call code pipeline is the fastest, and overall, even the forced interface signature pipeline is pretty snappy, especially when compared to reflection, which is more than 6 times more expensive than the direct call approach. This is including steps that were taken to avoid additional allocation overhead. Please take these results with a grain of salt. These are very simple functions, so the overhead of reflection is relatively high. More expensive functions can make the extra overhead entirely moot, so don't disregard reflection without running your own benchmarks. Next, I wondered if it was possible to combine these two approaches. Whether we could get the performance closer to direct invocation without needing to rewrite everything to take in interfaces everywhere. What if I just wrapped everything? It doesn't change much right now, but it does illustrate that we can adapt our type signatures from the type-eliding interface approach and use type assertion to pass our functions the right arguments. Please note that this still doesn't provide compile time type safety, since we're passing through runtime type checks. We can get back to our normal functions, though, if we make a universal wrapper. Switch call uses a type switch to figure out which type of function we're calling, and then type asserts the parameter to match. Now, instead of writing a wrapper per function like we had before, we have a generic way of invoking them. This is powerful since the same case in the switch statement is usable by multiple functions. If we call through the wrapper, we don't need to rewrite our code. We just need to add new cases and type assertions to the switch statement. One interesting thing to note, while we need to type assert parameters, we don't need to type assert returns. The return values automatically become wrapped as the empty interface. Next, these two cases both take in float64s, but return different types. We can't combine them into the same case, though. Go doesn't let you use the fall-through keyword in type switches, and it doesn't support relaxing the asserted type of the functions, even though the written code is identical. On the other hand, if Go supported covariance, that is, if it let you relax type signatures for more specific ones to more general ones, like interfaces those types satisfy, we could possibly use that to make our code a bit simpler. However, I think that's probably the wrong direction for Go to take, as it makes it much harder to understand code. So I won't cover that further. But bringing things back, how does this type switch caller perform? Not bad, actually. Less than twice the direct approach. It's a bit heavier compared to our empty interface-based pipeline, but given that it makes our functions easier to read, I'm satisfied with that. But I'm less satisfied with needing to continually add to a giant type switch. Since we've lost the safety of our compile time type checking, we could add a new function that can't be handled by our existing switch, and the pipeline could run a long time before it hit a case that it can't process, causing a runtime failure, which wastes compute spend and my time. This is not ideal. So how do we fix this? Let's start with the failure case. The worst thing our code can do isn't processing everything slowly, it's failing outright at a later time. We can solve this with reflection, and put the reflection code we used before and used that instead of panicking. Replacing the default case with reflection means our pipeline will continue to execute even when there's no additional specializations added. I've also thrown in handling the empty interface signature to really cover our bases. With both of these, this approach is resilient to changes elsewhere. There's little wrong with safe defaults. On the other hand, if performance is our main concern, we can go a bit further in our quest for generic invocation, especially if we want to automate some of this work away, and we can quickly verify if something won't work efficiently before we've wasted too much time. In one of the earlier Go generic blog posts, Why Generics, it said, generic programming enables the representation of functions and data structures in a generic form, with types factored out. Honestly, this sounds like we're laying out a template for our code, and filling in the blanks with the right types. Just because the compiler won't template things for us, though, doesn't mean we can't do it ourselves. Let's change up our code a bit further so we can apply this insight. If we cut our switch call down to the bare minimum, each of those cases in the type switch is really just type asserting the function call, and then type asserting the parameters. And if perhaps we make it a method on a struct, we can avoid repeatedly type asserting the function on every call, which could save us some compute. This might give us something very useful to start with. This template isn't valid Go yet, but it does let us know what we can do to turn it into useful Go. If everything in our template looks like that, we can safely hide it in an interface. The caller interface is essentially the method version of our fun interface from earlier. Before we get fancy, let's try this approach out with our example function signatures. It's pretty straightforward to do the substitutions as needed. So let's see how it performs on the benchmarks. Oh, that's not better at all. But honestly, that should be expected. We aren't using the struct properly yet. Here's what that pipeline code looks like. Every element we pass into the pipeline is doing that work of wrapping the functions. Instead, we can do that once per pipeline. by constructing them ahead of time and passing them in separately. This brings the benchmarks back down to within 2 times the direct approach, which is great, but we need to do 1 or 2 more things before we can really automate. If I haven't telegraphed it enough, now we're talking about pattern 4, code generation. Code generation is using code to write code. It can get pretty advanced, using a separate tool to statically analyze your code and generate new code from it. But since I don't have much time left in my slot, I'm going to do it the quick and easy route and instead have my pipeline generate code for the functions that don't have one of these adapters yet, and print out that code in the error string instead, so I can paste it in for the next run. So let's switch to the demo. And time to go off script, so please bear with me. So you can see some of the code we had before. Here's some of the manually written calls. And here's our wonderful caller adapter pipeline here. But to get to the next part for code generation, first we need a place to put things. So we're going to make a registry map here. It's just a regular map with that takes in factory functions that generate callers. The key of the type, the key is the string version of the type signature of a function. Register maker is how we register things into the map. It has a little bit of a convenience thing, and I'll cover why we do that in a moment. Otherwise, it just adds things to the map. Make caller is actually the business end for this chunk of code generation. It will type assert the function we pass it in. It will check the map to see if a factory exists, and if so, uses it. Otherwise, it populates this data structure with some quick and easy names. So in this case, because we're only dealing with a very specific function signature with 1 in and 1 out, we generate a very simple name using the actual types of those strings, or the actual names of those types. We pass in the input type separately so that we can use it for type assertion, because we don't need to type assert the output types. And for additional convenience, we also get the type signature of the function. Then we pass them to our template and print it out as an error. So caller data is just an ordinary struct that takes 3 string fields. And then here is our template. A lot of this should look very familiar to the code we saw before. Since we needed to use the name a lot, instead of just passing in the input and output type raw, I switched everything up so to use a name and the function signature explicitly to make things quite a bit simpler. We have our call interface so that this becomes a it satisfies the caller interface. And then we have our factory functions, which I'm just calling makers. Finally, it also produces an init function to actually register the maker for us. We can get away with this because Go allows you to have any number of init blocks in a package. Oh, whoops. Didn't delete all of that. But let's remove that and go to the terminal. Oh, I also forgot to clear that. No peeking. But when we first run the benchmark, it generates the code for us and prints it all out. So let's just copy that, go back to VS Code, paste that in, save. The benchmark, you can kind of see off to the side here, is just wrapping or getting us our little pipeline with just this empty interface slice of all our functions. We go through the process of wrapping all of our functions and callers to actually print out the generated code. We collect all the errors, and then if there are any errors at all, we print it out. Otherwise, we just run a quick little benchmark function. This matches the ones I did earlier, but is a little tidier for convenience. So let's go back to our terminal and run run the code. Hey, would you look at that? Not too shabby. So this, to be clear, is definitely not production code. It's here for demo purposes. If you have two functions with the same signature, the copy-paste thing won't work, and the non-primitive types will break name generation. But I did write production code for this a year or two ago for the Apache Beam Go SDK. It uses static analysis to get the type information instead of reflection, and it's a script you can run with Go generate. You can find it on GitHub if you're curious. And so we come to the end of the retrospective. The takeaways from this talk, in my experience, are that when you're trying to write generic code in Go, especially generic execution code like I did here, you end up with a lot of code that isn't as clear, or it's just kind of inconvenient to use compared to the direct approach. It takes a lot of benefit to replace the loss of compile time type errors. And right now, it's much harder to do instead of simply writing straight Go. You can replace some of the compile time errors with earlier runtime or earlier type checking that you do at runtime. But yeah, looking to the future though, we'll have generics, but also right now we do have a tool to try them out. So if you look here, we have our wonderful caller interface, our example functions as they were before. But what's new is we have a generic version of our template here, where it takes in the input type and the output type, which can be any type at all. It's got one method, which allows the wrapper here to support the caller interface. We have our same map here. Our register function can also become generic, which means it can handle one-by-one types. And instead of having a maker function for each time, we can just have a closure that generates the correct thing just in time. We have a make caller thing similar to before, where it just looks things up in the map and then executes the wrapping. And we can then also have a our caller pipeline is exactly the same as before. We just, call some very quick and easy manual registrations over here. And then we can just execute the pipeline. Not bad, eh? So, overall, I think with generics, we can do better. And in my case, I certainly won't need to run Go generate anymore. Thank you, Go WestConf. I've been Robert Burke, and this has been Go Without Generics, a retrospective. Please enjoy the rest of the day and have a wonderful weekend. Thanks for watching.